Okay, so let's take a look at 6.4, electronic structure and electron configurations. So before, we just finished talking about the set of quantum numbers that we have. Again, don't be alarmed by the old idea of quantum numbers. You have principal quantum number n, goes from 1, 2, 3, 4, all the way out to infinity. And this is, again, the energy level or the size, or really what we call this is the shell. And then once you break it down into shell, the next thing is going to look at L, which is our subshell. Our subshell goes from 0, 1, 2, 3, all the way out to n minus 1. This is going to be the shape or the wave function. And this is going to be the subshell. Each of these subshells have individual m sub l's, which go from negative L through 0 to positive L. And these are going to be our individual orbitals. I guess I should keep it consistent. These are going to be the direction of those shapes from the previous. These are going to be our orbitals. And each orbital is going to have two sets of electrons, plus 1/2 or minus 1/2, or spin up, spin down. So just to further clarify these, again, L, S, P, D, F, G, so on and so on. This is plus 1/2 is spin up, minus 1/2 is spin down, and then the L values are kind of the number of orbitals. So ultimately what the m sub s leads to is the number of electrons, but ultimately 2 electrons per orbital. Okay, so now we're going to actually apply this practically. So if we look at orbital diagrams, what we're going to see is things are not clear cut. It's not like I fill all of the n equals 1s and then 2, then 3, then 4. It is ordered based on energies. And so what we're going to see is if we look at our order here, our 1s is the lowest, and then 2s, then 2p, 3s, 3p, 4s, and then 3d fills. So if we're just highlighting all of the values of n, right? So 1, then we have 2, there's my 3, there's my 4, actually one more, 2, 4, let's see here, what haven't I used yet? Yellow, and then there we've got 5, so on and so forth. So those are all the values of n, and then the individual L's and subs. So again, n is all of the highlighted ones. And then if we look, the S, the P, the D, the F, those are my L values. L equals 0, L equals 1, L equals 2, and L equals 3. And then these individual orbitals here, these individual orbitals here are going to be the number, actually, I guess I should say these individual orbitals here represent, do it this way. Those individual orbitals represent the m sub l values. So this would be -2, -1. This way, here we go. -2, -1, 0, +1, +2. Those right there are individual orbitals, or individual m sub l values are my orbitals. And each of these individual orbitals, I'll just use the one above, each of these individual orbitals can hold 2 electrons. Okay, so when you look at the top here, the total number of electrons that fit, that is based on the number of L times m sub s, essentially. And it's not really m sub s, but times 2. The total number of m sub l's times 2, because 2 electrons can fit into each orbital. So a d can hold 10, a p can hold 6, an s can hold 2, and f can hold 14. So ultimately, you don't need to memorize any of this because it's all going to be, you're going to be able to pick it out of the periodic table. So we're going to take a look at that in just a second. So there's a handful of rules when you're filling these things up, and I'll show you how to correctly read them based on the periodic table. So again, let's take a look at the notation. The 1 out front, that is the value of n, or the principal quantum number. The subshell, that's going to be my value of L, coordinated 0, 1, 2, 3, again, S, P, D, and F. And then the total number of electrons in the subshell is going to essentially be, well, the number of electrons that fit in the subshell. S can fit 2, P can fit 6, D can fit 10, and F can fit 14. Those are the total number of electrons. But remember, there is 1 orbital for S, 3 orbitals for P, so there's half a number of orbitals. Okay. So the first principle, the Aufbau principle, the German term for building up, or German for to build up. Electrons occupy the lowest energy subshell available. Basically, it says, when I fill this up, I am going to fill the 1s, then the 2s, then the 2p. So 1s fills, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d. So we're filling in order of lowest energy. It's not like I'm going to fill this and then start filling a 4p. That's not allowed. The Aufbau principle basically says just fill the lowest first. And we're always going to do that. The periodic table is going to help guide us. Hund's rule, the lowest energy configuration for an atom is when electrons within a set of degenerate orbitals. So that's an important word, and I'm going to use that quite a bit. Degenerate orbitals. So if I have a 3p, again, p is representative, L is equal to 1. Therefore, my m sub L values are -1, 0, and +1, meaning I have 3 orbitals. So for my 3p, I have 3 orbitals. These things right here are what we call degenerate. Degenerate is just a fancy word for basically saying these are the same energy. They're degenerate, they all are the same exact energy. So the lowest energy configuration is where electrons have the maximum possible of unpaired electrons. So when you're filling this, that is what it looks like. Not I'm not going to pair up electrons until, again, in a degenerate orbital. I'm going to pair up after I fill up individual ones. So we always fill individual ones before we pair up. And there's a reason for pairing energy. It costs extra to put an electron next to another electron versus just putting it in a degenerate orbital. So this is not so much. We're going to avoid that. This is correct. Okay. All right. And then the other one is the other rule where we can't have the two sets of the same sets of quantum numbers. Yeah, so you can't have 2 electrons with the same spin. They always have to have opposite spins when they're in the same orbital. And we talked about that already, but we'll talk about it again briefly. All right, so let's take a look at some really simple ones. Give the electron configuration and orbital diagram. This basically means we're just using those little lines. So hydrogen 1s is the first thing that fills up. Hydrogen has 1 proton, and therefore when it's neutral, it has 1 electron. So 1s, there is the electron configuration for hydrogen. In fact, I probably should change this. 1s1 and with the orbital, so that's the electron configuration. The orbital diagram for this is going to look like so, 1s. That's the orbital diagram for hydrogen. For helium, it is going to have 2 electrons. So 2 electrons, again, 1s2, there's the electron configuration. The orbital diagram is 1, 2, and we're going to pair those up. Give the electron configuration and orbital diagram for carbon. So carbon has a total of 6 electrons. So the first thing that is going to fill up is the 1s, and we can fit 2 electrons in there. So I have 4 electrons left. This is my electron configuration. Next thing that's going to fill up is the 2s, and that's going to have 2 electrons. The next thing that's going to fill up is the 2p, and that's going to have 2 electrons. The 2p can fit 6 electrons, but I have 6 total electrons. So 2, 4, 6 electrons, and I'm out. So 2p is going to be partially empty because we don't have enough electrons. So let's take a look at the 1s, 2s, and now my 2p has 1, 2, 3 orbitals. Again, if I were to look, the m sub l values for these, so this is 0, this is 0, this is -1, this is 0, and this +1. The L values for these, that is 0, 0, and p is equal to 1. And then the n values are out front. So n equals 1 for this, n equals 2, n equals 2 for the rest of those. Okay, so we can always determine the quantum numbers, which we're going to do in just a second. So we've got to put in 6 electrons. 1, 2, 3, 4, 5, and the next one, we're going to keep it unpaired to follow Hund's rule. Okay, so 6 electrons. There we go. So let's take a look at this one quickly. What are the quantum numbers associated with that electron? So with that electron right there. Well, n is equal to 2. L is equal to 1. Again, that's the p orbital. M sub L is equal to, in this case, I have it written down as 0, and the M sub S is +1/2. So we can always assign quantum numbers to these. Good. So that's pretty much how we're going to assign quantum numbers. So maybe I'll go over this in class, but what are the quantum numbers associated with just one of these 2 electrons? Let's say this one right here. What are the quantum numbers associated with that electron? Actually, pause it. No, do it quickly, just so we don't have to do it in class. So pause it. What are the quantum numbers associated with that electron? Okay, n is equal to 2. L is equal to 0. M sub L is equal to 0. M sub S is equal to -1/2. And we're going to do a bunch more of these, but that's the idea. Okay, so that's electron configuration. So how did I know that the 1s fills, then the 2s, then the 2p? It's the lowest energy. But what we're really going to do is we're going to take a look at a periodic table. So please pause this, grab a periodic table, or get something you can write on, because this is going to be not really long-winded, but it's certainly going to be an important part of this. Take a look. So I'm going to divide the periodic table. I'm going to highlight some of this stuff. And so let me pick orange there. All right, so I'm going to highlight this right here. I'm going to divide the periodic table up a little bit. Okay, this section right here. Next up, I'm going to take this over here. Helium is a little weird. I'm going to move helium right next to hydrogen. And there's a reason for that. It does belong where it belongs, but just for the sake of having this conversation, helium belongs next to hydrogen for this conversation. Okay. Next up, we'll do this section. So this set of electrons right here. Or sorry, this set of elements right here. This is all the D block, which we're going to get to. But that's why I kept calling it the D block, because it has to do with electron configurations. And then finally, the groups down here, which we don't really see a whole lot of, or we don't use a whole lot of them in this class, but okay. So let's take a look. Again, I'm going to move helium over to here. So this first block here, the orange block, this is known as the S block. The value out front is going to be equal to n. Well, what does that exactly mean? Well, what that means is each of these rows is going to correspond to a principal quantum number. Okay, so what I'm going to do is I'm going to say, these are the n values going down. So this entire first row is equal to n equals 1. This is n equals 2, 3, 4, 5, 6, and 7. So the principal quantum number for everything in this row is 1, and this row is 2, 3, 4, 5, 6, 7. So that's where we're going to start. So S block, meaning if this is the S block, this right here is the 1, and I'm going to draw all over this. We're going to get ourselves plenty of periodic tables to get this stuff done. This is the 1s, okay? In fact, I'm going to use a different color for this. And just switch to sure, let's try this. So this right here is the 1s. So this whole thing right here is the 1s, making this the 2s, 3s. Again, it's the number out front plus whatever block that we're in. So this right here, this is the 4s, okay? So 4s, 5s, 6s, 7s. Easy enough. Okay. So next up, this purple block here is known as the P block. And much like the other one, it's just n, whatever's out front. So we're going to switch this to, let's see here, let's try gray. It's a little hard to see. Let's try. Perfect. Maybe that works. All right. So this row right here is 1s, and there's no 1p. And we could figure out quantum numbers is going to tell us that. The 2 is going to have a 2s or a 2p. So this right here, all of that is 2p. This right here is 3p, 4p, 5p, 6p, 7p. Again, because the number out front represents the n of that block. So if this is 2, this is the 2s, this is the 2p. This is the 3, this is 3s, 3p. Next up, this blue one here is known as the D block. A little bit different, the D block is not n, it's n minus 1. So whatever number is out front, we're going to essentially subtract 1 from it. So if this is the n equals 4, that makes this right here n minus 1. So this becomes the 3d, making this the 4d, 5d, 6d. Okay. And the last little bit, the one we spend the least amount of time in, this is the F block. F block is going to be n minus 2. So we have to kind of take just a moment to recognize the fact that what are the numbers that are out front here? Well, once we finish barium is 56, notice that we go then down here, we fill this up, and then we come back up to hafnium. So this right here belongs right there, meaning if this is 6 out front, this is 6 out front here, and that's exactly where we're at. This is 6, this is 7. So if that is 6, what that means, if it's n minus 2, this right here would be the 4F. This is the 5F. Okay. All right. So in terms of how things fill, right, and we can actually make a list of the order of filling if we wanted to. Would be the order of filling is always going to remain the same. Okay, so the first thing to fill is hydrogen. So the 1s is the first thing that fills. So 1s. What fills after the 1s? And all we're going to do is we're going to go across, and we get to the end, we're going to start again. Start again. Start again. Start again. Start again. Okay, so let's just do the total order of filling. So 1s, go to the end, and then we start in the next line. 2s is next. What fills after the 2s? The 2p. So 2p is what fills next. After the 2p, we're finished. So we start again on the line 3. 3s, 3p. What fills after the 3p? The 4s. And then the 3D fills. So this is our first discrepancy. Notice that the 3D fills before the 4s, or before the 4p, which is going to be next. So it goes 4s, 3D, 4p. And what we're going to notice is if we go back to our original, that is in fact the same exact order. 1s, 2s, 2p, 3s, 3p, 4s, 3D. So we are seeing the 3D filling before the 4p. And all we have to do is recognize that if we understand how the periodic table works, we never have to know that. It's just going to fall out. So what fills after the 3D, 4p, then the 4p, we finish the line. So 5s, 4d, 5p. So 5s, 4d, 5p. What fills after the 5p? The 6s. And here's where it might get a little bit tricky. 6s, and this is the weirdest part. So 6s fills next, and we actually put in, so 1, 2, 3, 4. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. These two, most of the time, are written up here. And so I should actually add those LA and AC. So in fact, I should probably just remove those from there altogether. Weirdly, one electron goes into the 5D, 5D1, then we fill this, and then we come back and fill the rest of this, and then we continue on. So really what the next thing to fill though is going to be the, so after we fill the 6s, we're going to fill the 4f, then the 5d. So 4f comes next, then 5d, and after the 5d comes 6p, and on and on and on. We can do the rest of it, but we're going to do a bunch of these examples. Okay. Okay. How many electrons fit into each of these? And so that's the last little bit that we're going to add here. So it's really easy to do because what we're just going to do is we're going to count the total number of elements in that line. So how many electrons fit in an S block? We know that S has one orbital. And a total of 2 electrons can fit in there. Again, we know that 2 electrons can fit because we have, in fact, just 2 elements here. How about the p block? Again, the p block is going to have 3 orbitals for a total of 6 electrons, and we can count them 1, 2, 3, 4, 5. There are 6 elements in that row, so we know that there's going to be 6 electrons that fit there. The d block is going to have 5 orbitals or 10 electrons. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons fit there. Okay, I don't know why it's delaying. 10 electrons, there we go. 10 electrons fit there. And then finally, the 4f, there are 7 orbitals, 14 electrons. Okay, and if you count them, cerium all the way to lutetium, you have 14 elements in that row. Okay, all right, so that's it. That's how we're going to fill these things up. So if we give the electron configuration for potassium, all right, well, potassium has, and let's take a look, potassium has 19 electrons in the neutral state. So if it has 19 electrons, and let's do both the orbital diagrams. So first of all, 1s2, what fills after the 2s2, 2p6, and 6, 7, 8, 9, 10. I have a total of 10 electrons. So I'm sorry this is delayed so much. I don't really know why it is. It's coming. So 1s2, 2s2, 2p6 for a total of 10 electrons. I don't know if it's delayed for you or just for me. Maybe I'll just pause this for 1 moment. All right, it just recorded it. So, or maybe we're gonna be good now. All right, so we have a total of 10 electrons. Count the numbers of the superscript, right? 6 from the P, 2 from the S, and 2 from the 1s. So a total of 10. So we have 19 more electrons. So what fills next? Look at your periodic table. We're gonna notice that the 3s, right? Potassium, the next is the 3s. It's gonna put 2 electrons in there. And then the 3p, 6 electrons in there. How do I know 6 electrons go in there? Count the number of elements. Each element gets 1 more electron, right? So add 1 more electron. And then finally, 4s1. So 4s1 for the total number of electrons. So that's it. That's filling. That's the electron configuration of potassium. 1s, 2s, 2p. But of course, 2p has 3 orbitals, 3s, 1, 2, 3, 3p, and the 4s is next. So 1s, 2s, and then notice how I'm going to fill the 2p. Each individual one gets an electron before I pair it up. 3s, 3p, they all get individuals before we pair up. And then finally 1 electron in that 4s orbital. There we go, electron configuration and orbital diagram. So you give it a go for nickel, technetium, and calcium 2+. So let's just take a quick look at calcium 2+. Calcium 2+, this indicates that I have lost 2 electrons. So how many electrons does calcium have? And then recognize that we lost 2. So we'll just do these in class together. Anomalous configurations. So write out the configurations you're expecting for chromium and copper, and we'll talk about why it's wrong, essentially. And then we'll walk through all of these problems together. I think one other thing is diamagnetism, paramagnetism, ferromagnetism. We'll actually talk about this in class. And so let's not worry about that now. But yeah. This is it. One more section, and the next section is kind of the most important of the group. It's neat to be able to make electron configurations, but the next part is kind of where the properties all come together and why this is such an important concept.